Welcome to Part 1. In this part of the course, we will discuss some basic terms, concepts, and tools necessary for writing and running our programs. Before we get to the Java programming language, I would like to discuss what a program is in any language. A program is a set of instructions which can be inputted, understood, and executed by an information processing system, or IPS. What is an IPS? Well, to be specific, I define an IPS as anything which has the following characteristics. Some kind of input-output systems, like a keyboard, mouse, monitor, ears, eyeballs, or vocal cords, all of which can take information in and out of the system. It must also have some way of representing and storing the information in various forms, such as numbers, letters, images, sounds, and so forth. Finally, it must be capable of processing the information, usually to solve some kind of problem. Now that we understand what an IPS is, recall that a program is a set of instructions which can be inputted, understood, and executed by an IPS. Therefore, we might say that a recipe is just like a program which is executed by a cook. Similarly, if a person wants to improve their health, they can look up an exercise program, which is a set of instructions on exercises to achieve that goal. There are many different kinds of information processing systems, and there are many different kinds of programs. We will of course be focusing on programs written in the Java programming language. Now, it turns out that several steps are required for our Java code to actually be understood by a computer, and that is what we will look at in the next few lessons. Now that we understand what a program is in a general way, it is time to get more detailed about how computers are able to understand the Java programs we write. It turns out that several layers of translation occur before we can even execute or run our programs. After we talk about that, we will look at what happens when our program is actually running. In order to explain how computers understand the Java code we write, we need to know a bit, excuse the pun, about how computers represent information. As you may have heard before, most modern digital computers process and store information using zeros and ones, also known as binary. Now, this isn't a computer science course, but I want to be clear that computers don't literally use the symbols 0 and 1 to get their work done. Most digital computers typically use higher or lower ranges of voltages to represent 0 and 1 or on and off. The reason we use the symbols 0 and 1 as representations of something like a high or low voltage is that it allows us humans to use mathematics to understand, design, and manipulate our digital computers. If that did not make much sense, do not worry at all. The truth is, languages like Java hide most of these details from us application developers. The key point I was trying to make is that digital computers cannot understand high-level programming languages, such as Java, in their original state. Therefore, all high-level, human-readable programming languages must be compiled, which is another word for translated, into binary. The actual process to go from the Java code we will write to some kind of executable binary language is quite complex, so I will only give you a simplified overview. First, the Java code, which is written in files that have the .java file extension, are given to a program called javac, which is a shorthand name for the Java compiler. javac will take the code that we have written and reproduce it in Java bytecode files, which have the .class file extension. Once the Java bytecode is created, the next step is that the bytecode will be given to a Java virtual machine, or JVM for short. There are many different JVMs which are written for different operating systems, such as Windows, Mac, or Linux, and I will discuss them further in the next lesson. For now, understand that the JVM will take our class files and translate them into something which the operating system itself can execute. Fortunately, the programs we typically use to write our applications will handle jobs like compilation for us. Even so, it is helpful to know a bit about this process. What we just talked about explains what happens just before an application is deployed, and we refer to that time frame as the compile time in an application's lifecycle. Now we will talk about the time frame when an application is actually running on a computer, which we call runtime. At this point, I'm going to try to explain what happens in a computer when a program is actually running. Rather than describing this process using a bunch of big words, I will try to give you a visual way of understanding things. Now, in order to keep this appropriate for beginners, I will have to leave out many details on how the different parts of a computer, namely the CPU and the computer's memory, really work. Later on in your career, you may wish to study a book like Operating Systems 3 Easy Pieces to learn about CPU memory virtualization and other advanced topics. I want you to imagine for a moment that the memory of a computer is itself a virtual 3 or 2-dimensional space, kind of like a video game world. You might also think of it as being something similar to your own mental workspace, which you use to solve problems and design things. When your program is executed and runtime begins, an unused portion of the whole memory space is allocated or provided to your running program. We typically call a running program a process, in case you have ever looked at a task manager and wondered what the list of processes was all about. What gets created in this virtual memory space depends on the different instructions we have given to the computer via the Java code we write. For example, in the application I will be using as a teaching tool in several lessons, one of the first instructions, also known as methods, which is executed is called start. Do not worry about understanding everything going on here just yet. The only thing I want you to notice is these new keywords. The new keyword is one of the ways in which we create objects in memory space. I will revisit this word object later, but a good way to think about it is to imagine a real-world object such as a person. By the time these instructions have completed, all of these different objects, each which have different names and jobs I have given to them, are sitting in memory space, waiting for the user to start interacting with them. As the user begins to interact with them, they will start to send messages, crunch numbers, store progress, and begin redrawing the user interface appropriately. The main point of this lesson is to give you a way to think about your programs not just as a bunch of lines of text, but as a virtual world where different objects pop in and out of existence during runtime. You, as the programmer, dictate what these objects are called, what their structure looks like, what problems they solve, and the relationships between them. Thinking of a running program like a company full of employees or a bunch of little robots solving problems and sending messages to each other may help you to design your programs more effectively without worrying about the keywords and syntax until later. That's enough for now, but for a sneak preview, in part 5 of this course, I will teach you exactly how to design these little robots systematically and effectively. Before we proceed to learning Java, we need to talk about how to write and run it. This video is about different ways to write and deploy Java applications, along with their benefits and drawbacks. Believe it or not, it is entirely possible to write a functioning Java application using only a plain text editor like Notepad and a Java development kit, often abbreviated as JDK. You can probably guess what the text editor is for, but the JDK gives us two very important tools. The Java compiler program javac, which as discussed in the previous episode, will create our Java bytecode. Also a Java runtime environment, or JRE, which among other things contains a Java virtual machine which interacts with the operating system. So, do I recommend you use this approach? Almost definitely not. It is impractical for most graphical user interface programs and does not provide design time, i.e. before compile time, help with syntax and error highlighting. However, it is worth learning to use this approach as a good learning exercise, especially if you plan to work with Linux. An integrated development environment, or IDE, is a needlessly complex name for a program which you use to write other programs. As you have probably noticed already, us programmers have insecurities just like everybody else, and one of the ways they choose to vent that insecurity is by giving things scary, complex, and obscure names to make themselves feel smart. Let us talk about why almost every Java developer I know uses an IDE. They have a built-in text editor with design time error and syntax highlighting, as well as code completion. They usually have a built-in compiler and sometimes a built-in Java runtime environment. Creating, building, and managing projects is very easy. If for some reason you cannot set up or run an IDE on your computer and you do not want to torture yourself with Notepad and the command line, the next best option is to find an online Java IDE. If you search either Online Java Compiler or Online Java Editor in your preferred search engine, you will find a bunch of different websites which effectively provide you with a browser-based IDE. I will not recommend one in particular, but look for one with syntax highlighting and error checking. Being able to create multiple files would also be a big bonus. Just be cautious of malware and try to find one with a good reputation. There should be some free tools like that out there. If you are really serious about getting into Java desktop, web, or Android development, you will probably want to download a real IDE. Personally, I like to use IntelliJ IDEA, Android Studio, and Eclipse for Java development. I will be using IntelliJ IDEA with the dark theme enabled during coding lessons in case you're curious. Also, if you plan to get into Android development, definitely go with IDEA or Android Studio because Android Studio is based on IDEA. I know a few people who like to use NetBeans, but it would not be my first choice or second choice for that matter. You will likely also want to download and install either a JRE or a JDK. If you're using an IDE, a JRE is probably sufficient, but I would recommend grabbing the JDK anyways. Just as a reminder, the Java Development Kit is made for developers, whereas the JRE is basically just a way for anyone to deploy Java applications on their computer. A JDK will contain a JRE. The Oracle website is a secure place where you can download these things. A word of warning, setting up an IDE on an operating system is not always easy. Every programmer must deal with the issue of configuring environments, and even the best of us sometimes have to spend hours and even days solving these problems. Roughly half of what we do as programmers is we take real-world information and represent it virtually as data. In this part of the course, I will teach you how I actually use Java programming constructs for variables, constants, and complex data in my production applications. To give you an idea of what is ahead, how I represent such data depends on how often I expect it to change and how complex it is. Before we get to writing code, however, I want to clear up some confusion you might have over some definitions. Another sad truth about us programmers is that we tend to use one word for many things and many words for one thing. You will have to get used to this as a normal part of the study of programming, but as your teacher I will try to clarify as much as I can. In the English language, the word model has a very large number of meanings. It can be used as a verb, noun, or even an adjective. Similarly, in the field of software development, this word model has taken on many different meanings, and we will discuss two of them in this course. First, I will discuss data models in this part, and in part 5, I will talk about how this word relates to software architectures such as Model View Controller. When used as a noun, the word typically refers to what I like to call a data model. A data model is just a representation of some kind of real-world object, such as a user in a social media app, a note in a note-taking app, or a Sudoku board in a Sudoku app. One important question to ask is, how detailed should these data models be? Even something simple like a note could have a lot of details such as content, creation date, last modification date, character or word count, author, deadline, font, and so on. In part 5 of this course, I will teach you how to design these data models and how to make decisions about their detail based on the features you want your application to possess. For now, the short answer is that they should be as simple as possible, but no simpler. There are many different constructs in Java which help to model information. Some are simpler than what I just showed you, and some are more complex. In the next few lessons, we will look at the most common and most useful constructs with an emphasis on what kind of problems they solve in practical situations. Before we look at different ways to represent or model real-world information in our programs, it is important to understand a bit about how they work under the hood. By that, I mean the different ways they are represented and accessed in memory space. If anything in this lesson does not make immediate sense in theory, do not feel as though it will stop you from completing the practical parts of this course. Studying theory is one way to learn, but for many of us, myself included, writing the code itself is a better teacher. If you have ever studied algebra, then you should be familiar with symbols such as x, which represent some value. This is of course called a variable in algebra, and usually they represent some kind of number. Thankfully, in most programming languages, we have a lot more flexibility over what a variable represents. However, computers do not like surprises, so we must tell them ahead of time about what kind or type which a given variable will be. There are many different types of variables, but they can be categorized broadly into one of two types. For my ESL friends, yes, the words kind, category, and type can be used interchangeably, so I am basically talking about two types of types. Welcome to the field of type theory. At the lowest level, computers work with machine code, which we can think of as zeros and ones or binary language. Through clever manipulation of binary mathematics, we can represent things like negative numbers or floating point decimals using such mathematics. We can also use a technique called encoding, where we associate some particular character with a series or string of binary values. My point is that by using very basic things like 0 and 1, we can build and represent more complicated things. Thankfully, in Java and most other high-level languages, we do not need to work exclusively in binary. Java provides us with 8 different fundamental or basic types, which are known as primitive types. Those types can represent integers of varying sizes, floating point or decimal numbers, a single 16-bit Unicode character, or a Boolean which represents either true or false. Primitive types always start with a lowercase character, and this is important as the compiler will not treat them the same way if you use an uppercase first letter. It is also important to remember that these primitives take up varying amounts of memory space. Normally this difference is negligible, but if you would like to learn when it is not, then you will want to study a topic called asymptotic runtime and space complexity. This is a topic in software engineering and is outside the scope of this introductory software development course. In simple terms though, if you are dealing with enormous quantities of data, you need to be concerned about using the smallest and most efficient types for the job. Another kind of variable in Java is called a reference type variable. This particular name reference has been the source of confusion and many arguments for students of programming for over 20 years. I will address this confusion more in the next part of this course when we talk about functions and logic. The purpose of these reference types is when we want a variable which represents something not suitably represented with a primitive. That is a vague answer, but do not worry, we will be looking at many of these situations in detail soon. Two important differences between reference and primitive types are that reference types always start with a capital letter, or at least they should, and, unlike primitives, they store memory addresses instead of values. Before we move on, it is very useful that you understand how primitive and reference type variables work in memory space. Explaining this verbally is difficult, so I will use a simple visual analogy side by side with a tool that allows us to step through a program incrementally to see what the states of these variables are in memory space. Before I proceed, while I normally stick to practical code examples, this one is not useful for anything except to demonstrate variables in memory space. This first line creates a variable called firstValue, which is of type int. Since this type starts with a lowercase, it is a, take a guess, primitive type. This second line creates another variable called secondValue, which is of type integer. Since it starts with an uppercase, we know it is a, this one should be easy, reference type. This third line, age3, creates another integer reference variable, but something strange is going on, which we will talk about in a moment. This fourth line creates a char variable, short for character, which is also a primitive. I will now show you what is happening line by line in this program using a debugging tool called a stepper. It allows us to step through our code on a line-by-line basis. It also allows us to see what the virtual memory space of a program looks like as we step through it. Let us execute this first line. Our memory space is now populated with a variable called firstValue, and the value which it contains is a number, 26. Let us execute the next line of code. As you can see, variable secondValue just popped up in memory, but there is something different going on here. Instead of storing a number, we see a type and an address in virtual memory. If we go to that address, we would find the value 1, but the key point is that reference type variables store an address to a location in memory. After executing line 3, we see that a variable called thirdValue does exist, but the value it stores is null. Null is essentially a way of saying that this reference variable does not reference anywhere in memory. If we tried to access this variable later on, the program would crash with a null pointer exception, since it is like asking a computer to go to a place in memory that does not exist. Computers don't like that. Let's execute our last line of code to see what a car primitive looks like. Now, as you can see, our debugging tool is doing some extra work here and actually showing the capital A, but what is really stored here is the number 65. What does 65 mean? Well, if you look up a list of Unicode characters, you would find that the code for the capital A is in fact 65. I cannot count the number of times in my career when something did not make sense to me when explained verbally, but made perfect sense when I either looked at what was going on in the memory space, source code, or even generated bytecode. Keep that in mind and do not be afraid to invest the time in learning tools like the debugger. In this lesson, we are going to look at how to model and work with simple information. Before proceeding, please open up your preferred IDE or online editor, as I fully expect you to follow along with me by writing out the code examples. In the previous video, I used a debugging tool called a stepper to look at the state of my variables as they change during runtime. There is also a simpler and faster way to do this. Every running program, also known as a process, is constantly communicating streams of data between itself and the operating system. Using the system.out.println method or command, we can make use of one of these streams to print out textual data to a console or terminal. If you're not sure what a console or terminal is, it is the simplest way in which a computer and human can interact, via text. The most common type of variable we use for textual data is a string, which you can think of as a sequence of car primitives. String is a reference type, and most reference types require usage of the new keyword, unlike primitives. However, because string is used so often, even a verbose language like Java will allow you to cut some corners when creating them. Alright, now we will call the system.out.println method and give it our variable. Assuming your code is well formed, if you were to run it, it would print hello world to the console. One last change. As programmers, we always want to write the minimal lines of code and use up the least amount of memory as possible. If we wanted to, we can actually get rid of our variable entirely and just type our message directly into the arguments for println. Now we will play around with some numbers and simple math. Let us create two int variables. Now we will perform subtraction of them and store that result in another int variable. Now we will print out that result. Everything looks good, but let's try some division. Because we are using int type variables which do not support decimals, our divide result was rounded to the nearest integer. Let's make a few changes so that we are printing an accurate result. Now let's run the example. Much better. Now we will look at a practical problem. Pay close attention, as there will be a coding exercise I expect you to complete at the end of this lesson. Every program needs to have a starting point for execution. In Java and many other C-based languages, that starting point is a main function. Notice how if you change the main method in any way, the IDE will no longer allow it to be used as a starting point. Also notice that main accepts what looks like a string type, but there are some square brackets beside it. These square brackets can follow any primitive or reference type, and they indicate an array structure. Let us create an array to learn more about how they work. Great, now we are going to make the elements at index 1 equal to 2. Alright, now here is a trick question. Did I just set the first element in this array equal to 2? Once again, I am going to use the debugger to get an idea of what an array looks like under the hood. As you can see, this variable called integer array is associated with 4 different cells, or you can think of them as buckets full of data. Now let us execute the next line and answer the trick question from before. The answer is no, I did not set the first element in this array equal to 2, but rather the second element equal to 2. That is right, the index or location of the first element in an array is 0, and the second is 1, and so on. It is perfectly natural to be confused and even annoyed by zero-based indexing, but you will have to get used to it. There are legitimate technical reasons why this kind of indexing is preferred in arrays, but that is a topic for a different course. We are now going to combine our knowledge of int primitives and arrays together with a very useful programming construct. As you may have noticed, when I use the debugger, a program is executed in a line-by-line, top-down way. Keep that in mind as we take a look at this new construct called a for loop. I am going to ask you to type along with me here, and after that I will explain what we just did. Now normally we leave this all on the same line, but I am going to break this for loop up so that we can add some notes to different parts of it. The comments I just wrote explain what each part of a for loop is responsible for. In order to see how they work, let us once again use the debugger. A programming loop allows us to repeat or iterate a block of code. We can also modify the variables in the loop after each iteration. In this case, we have stated that we will add 1 to the index each time. Let us step through a few iterations so that you can get an idea of what's going on. As you can see, we are just printing whatever values are stored in this array for each index. Before we proceed, there is one more thing about arrays that I want to show you. Suppose that the indexes of an array represent a coordinate, which we will call x. It is actually possible to add more coordinates to our arrays and thus create a multi-dimensional array. We will now create a two-dimensional array, which is quite easy to do. The main difference here is that when we want to assign a value to an array cell, we must now supply what I will call a y value as well. Here's a simple coding challenge. Using what you know about array indexing, I want you to make the cell in the third column of the third row equal to 5. Pause the video now and give it a try. Be sure to actually run the code to make sure that you do not have any errors. Alright, if you wrote this, then you have the correct answer. Otherwise, you may have become another victim of zero-based indexing and been given an array index out of bounds exception. To be honest, even after 6 years of Java, I still forget this from time to time. You may have heard the term object-oriented programming and wondered what it meant. There are some more technical definitions of object-oriented programming that we will get into later. Like I said before, half of what we do as programmers is to model information as data in virtual systems. In OOP languages, our goal is to group information, such as primitives, together as objects, and we can even add functionality or other objects within these objects. Let us take a look at some examples to expand this idea. Now that I have shown you some basics of the language, I am more and more going to teach you things using direct examples from the demo Sudoku application. If you are not already familiar with Sudoku, you will probably want to pause this video here and spend a few minutes learning the basics. The rules and structure of the game are very easy, which is one of the reasons I chose it as a demo. In keeping with what I just said before, our first task will be to model a Sudoku puzzle as a virtual object. We can do this by using a class, which is a special data structure. If you're working in a real IDE, then you will want to open up or create a new project, as I will ask you to create files. If you are using an online browser, just start with an empty editor. As you can see, we already have a basic class declaration here, which includes an access modifier, public, which we will discuss later, and the name of our class, which corresponds to the file name. Now, it is important to understand that I figured out the structure of this class ahead of time using techniques that I will teach you in part 5. Anyways, I decided that there are two data structures which are necessary to virtually represent a Sudoku game as a virtual object. The first was the actual puzzle itself, which I decided to model as a two-dimensional 9x9 array. For now, ignore the private keyword. I will explain access modifiers in due time. Now, the other thing I decided is that we want some kind of way to represent what state the game is currently in. I decided that 3 potential states might be useful: new game, active game, and a complete game. Here's a question for you, and this time there is not really a specific right answer. How would you represent these different states? Pause the video and think about it for a second. Some of you may have decided that you could represent the different states using integer values, maybe 1 for new game, 2 for active game, 3 for complete game. Some of you may have decided that using strings could also work, since you could actually write out each state in a very legible way. Whatever approach you thought of, they all have different benefits and drawbacks which must be considered. Since this is a very small application and I know memory consumption will not be much of a problem, I decided to use a data structure called an enum. As you can see, it looks a lot like a class. Let's add some entries to this enum. Now that we have built it, let me explain what an enum is. An enum allows us to create a restricted set of constant values in a very legible way. The important thing here is that we have a situation where we know that an object will be in one of 3 states, and we know what all of those potential states are, and we do not expect them to change much. Now, enums are not the most memory efficient tool for the job, but the benefit of them is increased legibility, and we will see later on that they can make it easier to read and control the flow of our programs. In a previous lesson, I said that there are 2 types of variables, primitive and reference, but also that there are other types. A variable, which sits in the body of a class, is referred to as a member variable. It is a member of that class. At the moment, I have not initialized or created these 2 variables. The most common way to do that is to use a constructor method. The simplest way to create a constructor is to type the name of a class followed by parentheses and curly brackets. Note that to create a proper constructor, the name of it must match the name of the class exactly. Now, we can also include an optional access modifier, and 95% of the time you will want that modifier to be public. Again, I will talk about those more later. Sometimes we want this class to be given the values we will assign to our member variables, and sometimes we want to create those values from within our constructor. In this case, I want the values for game state and grid state to come from an external source. These 2 variables here are what we call parameter variables. They exist only as long as the program is executing that particular method. Basically, what we want to do here is use these parameter variables as temporary containers for values which we will assign to our member variables. Now, I can actually give these variables whatever name I like, but by convention we usually give them the same name as the member variables we will be assigning their values to. Now, this presents a problem because if they have the same name, the compiler will not know that I want to assign the values to my member variables. To fix this problem, we can use the this keyword, which will tell the compiler when we are referring to this class, a member of this class. We've already seen some different access modifiers, public and private, and also seen that they can precede variables, classes, enums, and methods like our constructor. The rules behind these access modifiers are pretty simple, but it is important that you understand the motivation behind them. As I said before, in OOP, one of our goals is to group related pieces of information together in objects, and we have seen that classes are a way in which we build and design such objects. If we pretend for a moment that each of us is a human object, it makes sense that we want to have restrictions on what kind of information we share with each other. Some things we keep private, some things we share with a limited number of people or organizations, and some we make available publicly. Now, there are 2 reasons why we should decide not to share something. Firstly, some information about us, if we share it publicly, could be used by malicious individuals or organizations to harm us financially or otherwise. Secondly, it might also be the case that some information simply does not serve any purpose to share publicly. In fact, it might be a little bit detrimental. This is not just true about information we can think of as variables, but also behaviors which we can think of as methods like our constructor. To return to Java, there are 4 different access modifiers. Public is accessible by any software entity which is capable of pointing or referencing to that particular source in virtual memory. Usually this will be other objects from within the same application, but it is also possible in certain circumstances that it could even be an external application. Protected, aka package private, is accessible within any software entity that is within the same package, class, or subclass. Not including an access modifier defaults to visibility within the same package and class, but not within subclasses. Private, the most restrictive type, only allows information and behavior to be visible within the body of the class itself. The general rule for access modifiers is that you should always use the most restrictive modifier possible that still allows your program to function properly. In Java, by convention, we always make member variables private. The reason for this can be summarized by the following principle. An object should always have control over how external software entities access and change its member variables. With that being said, this class would be pretty much useless if we had no way of getting information in and out of it. To solve this problem, we use what are called accessor methods, also known as getters and setters. We can make the method public so that any software entity can access it. If we wanted to, we could include some kind of access restriction or check which an external entity would have to pass in order to get a hold of this data, but it is not necessary here. You will spend a lot of time writing these sorts of accessor methods, and any half-decent IDE will include a way to generate them for you. After clicking inside the body of this class in IntelliJ IDEA, I'm going to hit Alt-Enter. I'm going to select Getter and Setter, but also note that you can auto-generate a constructor, which is another option I use frequently. I then select the appropriate member variables for which I want to generate my accessors and then hit OK. There you have it. In this short lesson, I am going to introduce to you the idea of immutable versus mutable and why these big words are important. Even my native English-speaking students are possibly not familiar with these words, so I will start by defining them. Something which is immutable cannot be changed. Something which is mutable can change. It really is as simple as that. With that being said, although the word immutable technically means something which cannot change, such as the laws of physics, I suggest that you think about immutable and mutable as being a spectrum, rather than thinking about them in the strictest sense of the words like a binary on-off situation. A key term you will want to become familiar with is shared mutable state. In case you are wondering, state is, in a general sense, just another word which describes information represented in a mechanical or digital computer. Like I said before, we all seem to use one word for many things and many words for one thing. There's no need to code along with me here, but please pay full attention even if this is a silly example. I am going to use the Sudoku game data model from the previous lesson. I have also created a new Java class called sharedmutableState.java and set up my main method as an execution point, as well as a class called Sudoku Checker, which helps to verify if a Sudoku puzzle is complete. So here's the situation I want you to imagine. You're building a Sudoku app and your current task is to write some code which will test different methods from the Sudoku Checker class. Because you learned from Ryan Kay to test your code frequently in part 4 of this course, you decide to create a test version of a complete Sudoku game to test against the Sudoku Checker's methods. Sudoku Checker has a method called TilesAreNotFilled, which is supposed to return false if every tile has a non-zero value. This is one of several victory conditions for a solved Sudoku game. To make sure things are working properly, you set up a debugger to see what happens. First, you see that the value stored in TilesAreFilled is false, which is the expected value, but you also decide to check the state of the Sudoku's grid. And sure enough, we see that every cell is now equal to 0. You decide to use the debugger's step into function, which will allow you to dive into the code at the call site of a method. You see a normal two-dimensional array traversal, but it also has a line after each check that resets the value to 0. The obvious solution here is to remove the bad line of code in the problem method. However, there is actually a bigger problem with the overall design of our Sudoku game that we need to address. The problem here is that we have a mutable data model which is referenced in a number of different places. In this case, it was an external method, meaning a method defined in a different class, but this problem could even occur within the same class or even the same method. This is just one example of how shared mutable state can cause unexpected side effects. One thing we can do to protect our code, in particular our data models, from these side effects is to make them more immutable. One simple way to achieve this is to use the final keyword modifier. Here I have a version of the Sudoku game class which is closer to what you will see in the working Sudoku game demo. I have made two important changes to it. Firstly, I have made its member variables final, which means that after this object is created, these variables become read-only. Except for the constructor, this prevents any internal or external code from changing the game state. Now, I have also made the grid state array final or read-only, but there is a special case here to do with arrays. Making an array final will prevent someone from reassigning that array to a new one, but it does not actually make the elements in that array read-only. In effect, the reference variable grid state is read-only, but the underlying data in memory can still be messed with. The most convenient way I could think of to solve this problem, given that I still need some way to look at the state of this array, was to make it so that every time I needed to get that state, I create a copy of the state in a new array. This means that no matter where this data model gets passed around, it cannot be changed. When I first heard this idea of using the final keyword very frequently, I wondered, how do I work with data models that do not change? After all, logically, they must still have to change at some point, otherwise the program would be useless. The key to solving this problem is to create a new data model from the old data model each time a change is required. Remember, final variables can be set when we call a constructor. If you have a look at the Sudoku code demo, you will notice that I do create new immutable data models this way quite frequently. If you're worried about the memory usage, the good news is that the JVM has this handy garbage collector, which will find objects that are no longer referenced and free up the memory space they took up. Sometimes we have data which we do not expect to change during runtime at all. For example, the boundaries for x and y of the grid are both 9, as it is a 9x9 grid. Not only do I not expect this to change, at least for the first release of this app, but I also know that this value 9 is going to be popping up all over the place in the part of the app which builds a new puzzle and verifies a complete puzzle. With that knowledge in mind, I decided to make a static final member variable called gridBoundary. By convention, we like to write static constants in all uppercase. Here in the GameGenerator class, you can see this constant being used all over. Apart from making things more legible than just hard-coding the value 9, there is another benefit to doing this. Let us say that later on I decide to change this program to create a 16x16 Sudoku puzzle. In that case, I would only need to change the value in one place, and in every spot where this variable is referenced, the value will now be 16. That is a lot more efficient than if I had just hard-coded 9s everywhere. Now, I have kept this discussion very practically oriented because the truth about how static variables actually work is actually tricky to understand. I will revisit the static keyword in part 3, but there is one thing I want you to be careful with. We can actually remove the final keyword from this variable to make it mutable. In fact, if we wanted to be able to switch between 9 and 16 at runtime, that would be one way to solve that problem. However, I want you to be very careful using non-final static variables because that most definitely fits into the category of shared mutable state. Before we move on from the topic of modeling data, I wanted to talk about different options for long-term storage. A general term for this topic is persistence, which refers to persisting data longer than just the runtime of the application. There are many different ways to persist data in this way, and it mostly depends on the scale of the data, how efficient the storage needs to be, and in truth, your skill as a developer. Now, my goal here is just to overview things, as these topics can get very complicated very quickly. Two words you will hear in discussions on persistence are local and remote, or instead of remote you might hear the word cloud. Local storage simply means that you are storing data for the application on the device which executes the application, the user end device. Both remote and cloud simply mean that the data is stored on some other device. There is no cloud, in case you are wondering. In general, you have two options for storing data locally on a typical operating system. The simplest way is to use the operating system's file input-output streams, which are usually easy to access in Java. In my Sudoku application, I only plan to store data for a single game at a time, so I use this approach. Update game data writes a Sudoku game to local storage, and get game data reads from local storage. If it turns out that a file matching the game data is not found, I throw an exception, which is just a convenient way to know if I need to create a new game entirely. I will discuss exceptions more in part 3. Let's talk about some pros and cons of local file storage. It's usually good for small amounts of storage, often fast and easy to implement and use, and it can be fairly cross-platform compatible. The primary issue with it is that it's not very scalable. Another approach you can use is to create a database. Most databases are written in structured query language, or SQL, or some derivative language of SQL. An easy way to think about these tools visually is that they are basically just spreadsheets. Another common solution is to use an object database, which does not necessarily work like a spreadsheet. There are different ways to implement an object database, so I cannot give you a universal example here. I also cannot recommend one or the other in general. You will have to do your own research on what the current preferred tools are and what makes sense for the operating systems you wish to support. Local databases scale well among small, medium, and large datasets. Often they are very fast and efficient. They might require the operating system's read and write access, and they can be somewhat complicated to implement and use. Remote storage comes in the same types as the other options we have looked at, but the key difference is that your application will communicate, that is, send create, read, update, or delete operations to the remote storage system through a network connection or the internet. This comes with some great benefits, but also its own added set of complexity and potential problems. Since you are communicating over the internet, it follows that you will have to use some kind of tool to do that. Some benefits include users being able to share data across multiple devices. It can be made very efficient with a good internet connection. Some potential issues are that, of course, it requires the devices to have network access. Java does have some out-of-the-box tools to set this network communication up, but they can be tricky to use. In the previous section, we learned about various ways to represent or model information in computing systems, especially those running on a JVM. One thing which I have not stopped to explain yet are what we call in Java methods. In case you were wondering, this word method is another name for what we would call a function in most other programming languages. Other names we could apply to this concept in general include subroutine, algorithm, or even procedure. My goal is not to confuse you, I just want you to be aware that people in different languages and disciplines are often all talking about the same idea here. Speaking of the discipline of programming, if I was to give you a general definition for a method, I would say that it is a named set of instructions. Now, this lesson is densely packed with information, and I want to stress that while I did not include anything I thought to be useless information, I must once again ask that you not get discouraged if it seems like too much. Let us start with things that are absolutely necessary for any method, except for constructor methods, which we have looked at before. First, I will give you an overview, and then we will look at each part in detail. Every method must have at least 4 basic components: a return type, a method name, a parameter list, which can be an empty set of parentheses, and a method body, which refers to anything between the curly brackets. There are some optional things we can add, including an access modifier. Note that the same rules apply here if you do not give it an access modifier as with variables and classes. A static modifier. I will discuss this in the next lesson. There is also a thing called an exception list. which we will discuss later on. As you probably picked up on in the previous section, when you call a method, it can potentially return a value. Let us write a quick method to sum two integer values and return the result. Now, we can call a method and simply not assign a variable to the result. That is perfectly legal. However, oftentimes we want to be specific that a method is not intended to return anything useful at all. Maybe instead of returning the result of our sum method, we want to compute the result and print it to the console. The general rule here is that if the return type is void, we do not need to include a return statement. You can still use the return statement in this case, basically as a way of stopping the execution of the method. Most of the time, however, this is not necessary. Otherwise, our method must include a return statement, followed by a reference, or an expression, which has the same variable type as our return type. In our sum method, we do not actually need to create a variable here. We can just return the a plus b expression to save a bit of time and space. The last point I want to make about return types has to do with null. If your return type happens to be a reference type, such as a string, or even a primitive type array, we can also return the value null. Now, I will discuss error handling soon, but you need to be very careful about doing this. Sometimes it makes sense to return a null, but if the code which calls this null returning method is not aware that it can potentially be a null, then you will very likely crash your application. This practice of allowing null type references is commonly referred to as the billion-dollar mistake by the man who invented them. There is not too much to talk about regarding the name of a method. It works similar to a reference variable in that it is actually how we work with or execute a method. One thing to note is that apart from constructor methods, we always use camel case with a lowercase first letter. There are a couple important things to know about parameters which I will address in due time. However, the basics are very simple. The parameter list parentheses must be included even if they are empty. There is a maximum to the number of parameters you can include, but if you find yourself adding a great number of parameters, say more than 5, there is a good chance that you are not properly following the object-oriented paradigm. Now, one note is that a method name combined with a parameter list forms what we call a method signature. I will talk about this again when we look at method overloading. The method body contains what we call the implementation of the method. Implementation is a fancy word for the lines of code which are intended to solve some kind of problem. For methods specifically, the implementation really just means the lines of code between the curly braces. I will talk more about how to design methods properly in Part 5, but a hint is that we can call other methods within methods. I do not plan to talk about it much in this course, but there are certain cases where we can have a method which solves problems by calling itself. This is known as recursion, and it can be a very powerful tool. As I said before, variables come in two general types, that is, reference or primitive type. However, I also said that there are actually many different subtypes of variables in Java. I do apologize for having to teach you so much jargon here, but there is no way around it. As discussed when we talked about constructors, parameter variables refer specifically to those which we define in the parameter list of a method. Another term you will often hear is local variable. A local variable is defined within a method body. In either case, what these two types of variables share in common is that they only exist during the execution of the method they are local to. After the method completes, either by hitting a return statement or just the end of the method body, the memory space they took up is freed. The method's name and its parameter list constitute what is called the method signature, and you may not repeat a method signature which is defined in the same class. However, one can change simply the parameter list and reuse the same method name, as this constitutes a different method signature. This practice is called overloading, and a clear example of it can be observed with the system.out.println method. Using IntelliJ IDEA, if you click between the argument parentheses, which are defined by the parameter list, and hit Ctrl-P on the keyboard, IntelliJ will present you with a list of different possible argument types associated with this method name. This is how we are able to give various different argument types, such as integers, floats, strings, etc., to this same method. In case you are wondering about what the difference between arguments and parameters is, think of arguments as the things you pass into the method when you call it, and the parameters as being the variables we use to work with those arguments within the body of the method. Now that we have an idea of the basic structure of a Java method, there is something which is important yet difficult for beginners to understand. This topic has to do with what is happening inside the memory space of a running Java application. I am trying to make this course as practical as possible, but in this case the theory is a necessary component of what happens in practice. A common interview question for Java developers is as follows: does Java pass method arguments by value or reference? It is important to understand that even using the word reference here confuses the issue. In any case, if you just look at the code itself without knowing what goes on under the hood, it is reasonable to assume that we are passing references between methods. However, the correct answer to this common interview question is that Java passes arguments of any type by value. In order to explain why all variables, whether they are reference or primitive type, are passed between methods by value, we will look at a quick example in the debugger. Before that though, if for some reason you have skipped ahead and not watched the lesson in section 2 about what primitive and reference types are, go back and watch that now. In this class, I have created two member variables, one which is a primitive type and one which is a reference type. Again, this particular example does not practically solve any problems. I am just showing you about how the methods deal with variables. Within the constructor of this class, we call these two functions, printInt and printString, passing in our member variables. Note that because we are directly assigning these variables within the body of the class, they will already be created before the constructor is called. Let us use the debugger to see what the memory space looks like when we call these functions. At this point, we have not yet called printInt, but we see that primitive var and reference var exist in memory space. After proceeding to the next breakpoint, which is in the printInt method, we see that a new variable has been created and its value is 1. However, if I click on the This tab, which represents the memory space of this class, which contains our member variables, we see that primitive var and reference var still exist. So the point is, even though it looks like we pass primitive var into printInt from the constructor and it pops up in the printInt method, what shows up in printInt is a different variable which has the same value copied to it. If things are still confusing, let's change the name of the parameter and look again. See? New variable with the same value, passed by value. Reference variables work in much the same way, it's just that the value they copy to the parameter in the receiving method is itself an address in memory. As you can see here, once again we have two distinct variables, but notice that the address in virtual memory, which is what follows the @ sign, remains the same. Again, let us change the names to avoid confusion. Different name, but the same address value. Pass by value. One thing I like to do when I teach any high-level programming language is to point out useful distinctions between different concepts, approaches, and programming constructs which tend to appear in programs. In this lesson and the next, I am going to talk about two different kinds of logic that I observe in my programs. It is not necessarily the case that these two kinds of logic use different programming constructs. Instead, the distinction here is more about what kind of problems they solve. Now, I will use this word logic quite a bit, which is a shorthand way of talking about logical instructions, which can refer to a single line of code, a method, a class, etc. For now though, just think in things between the scale of a single line of code to the size of a method. The first kind of logic that I wish to discuss is what I like to call computation logic. Computation logic concerns itself with solving problems that have to do with the data in the application. Unless it is intermixed with the other kinds of logic, which I will discuss in the next lesson, computation logic can be readily represented in mathematical or algorithmic form. It follows that this makes computation logic not concerned about the broader details of the flow of any particular application, outside of calling methods related to crunching numbers, manipulating strings, or locating a value in a massive array. One of the interesting characteristics of computational logic is that it is very often interchangeable across different programs. This is especially true when the problems you are working with can be solved using only primitive types and reference types which come from the Java Standard Library. Now, you may have heard this term library before and wondered what it meant. In simple terms, a library is essentially some source file or set of source files which you can use in other programs, such as your own. Normally, these are things which have been written by other developers, but you can make and use your own libraries if need be. Every version of Java has what is called a standard library, which contains all kinds of different sources which can be used for building all kinds of different programs. For example, the classes I use to read and write the game data for my Sudoku application come from the java.io set of libraries from within the standard library, commonly referred to as the stdlib. There are two important takeaways from this lesson, one of which will become obvious after you finish part 5 of this course, the other of which you can understand immediately. Very often, when you have a problem which needs to be solved with some form of computational logic, someone has already solved that problem. Now, I am not saying that you should always use other people's solutions, as you can learn an incredible number of things by solving problems yourself. In fact, the older and better I get as a developer, the more I tend to prefer my own solutions. However, many of you who wind up working as developers in startups and small companies will have to get comfortable learning and implementing new libraries quickly. The second takeaway is this. Almost invariably, you will benefit from separating code which has different kinds of goals or concerns into different methods, classes, or packages of your application. I will revisit this idea in detail in part 5, as it is the essence of understanding good software architecture. For now, just take my word for it. Here's a coding exercise to help you avoid reinventing the wheel. In the project source code for this lesson, you will find a Java class called Coding Exercise Starter. In this starter, you will find a string variable s which has the following sentence in it. To refrain from imitation is the best revenge. You will also find a string variable answer which you will attempt to make s equal to. The code below the answer will tell you if you have succeeded or not, and you can verify by running the example. Before you proceed, listen carefully. To complete this lesson, you may not create any new reference variables. You may not directly reassign s to a new string. That would be a big fat fail. Your solution must compile, execute, and pass the equals test. You are encouraged to consult the documentation via your IDE or by visiting the Oracle documentation on the string class in the standard library. Good luck. Another type of logical instruction which you will find in a typical computer program is what I like to call control logic. Control logic is directly concerned with the flow and management of a specific program. Now, there is a subset of control logic which I like to call build logic, and this kind of code concerns itself with creating and wiring together different objects in the system. In this case, I am not talking so much about data models, but when we get to part 5 of this course, the objects I am speaking of will become clear. Control statements are used to direct the flow of an application in a logical way. They represent a form of decision-making capacity which allows programs to react appropriately to different states or data and potential problems, which we call exceptions. In this video, we will write out a few examples to learn and practice the basics. Most control statements make use of what are called Boolean expressions. I will not go into great detail here, but it is worth mentioning that Boolean algebra is one of the most fundamental and important concepts to study in the creation of digital computing systems. In any case, we will stick to Java-specific discussions. As discussed in the lesson on primitives, Java has a primitive type called Boolean or Boolean, depending on how you prefer to pronounce it. A Boolean may either represent true or false. You can assign a Boolean directly to true or false, but most of the time we assign the value based on some kind of Boolean expression. For our first Boolean expression, we will use the equality operator. Although most IDEs are good at catching this mistake, always be careful when working with the equality operator that you are not using a single equals sign. A single equals sign is interpreted as an assignment statement, and it can create some very unfortunate and unexpected behavior. We are now going to learn about the syntax for these keywords in Java. To keep our examples a bit more organized, we will create a new method. I am going to use some help from my IDE to speed this process up. Alright, so please keep in mind that some of these examples here are not designed to be optimal. This is mostly about new concept and syntax practice, but if you think you can fix things up and solve these problems in fewer lines, I think that would be good practice for you. So for those who are not aware, the absolute value of an integer is represented by its distance from 0 on a number line. Therefore, the absolute value of positive 5 is 5, and the absolute value of negative 5 is also 5. The first thing we will do is convert any negative values to positive values if necessary. To do that, we will check if the values are negative, and if they are, extract their absolute value using a standard library function. If the Boolean expression evaluates to true, we execute whatever is in the body of the if statement and we skip the else statement, and vice versa. Now, since the body of our statements are on a single line, we do not actually need to use curly brackets here. If you need several lines of code, you must use curly brackets. Sometimes you need to perform more than 2 comparisons in order to find the appropriate execution path. For this, we can use an if-else statement following an if statement. Let us finish off this method. Sometimes we want to be able to evaluate several Boolean expressions in a single if statement or wherever else we can use a Boolean expression. Let us write out another method which will be capable of checking the number of occurrences of a given character in a given string. We also want this method to be capable of handling null values for the string, and you will find that I love explicit method names. Okay, now we will implement that method. Now, if the string is null or it happens to be empty, then we know that occurrences will be equal to 0. Since both of these cases end up with the same result, we can combine them using an AND operator. We will also use the not equals operator, which does exactly what it reads like. The AND operator states that both expressions on either side of it must evaluate to true, otherwise it will default to false. There is another operator called the OR operator, which evaluates to true if at least one statement on either side of it is true. On my keyboard, I can write this operator by holding Shift plus backslash, which sits below my backspace key. Alright, to finish off this method, I am going to use what is called an enhanced for loop, or in other languages, a for each loop. It iterates through every element in an array or collection without having to mess around with creating and incrementing indexes. Let us code out the else statement since it is easy. I forgot to mention it earlier, but you can chain together as many else-if statements as you like. However, if you find that all of those if-else statements are performing some comparison on the same value, it is almost always better to use a switch statement. We are going to write another method which checks to see if any inputted integer is a power of 2. The switch statement starts by supplying some kind of variable as a predicate. Next, we supply a number of different cases, which the switch statement will use as comparisons to evaluate our expression. We can include as many lines as we want after the colon and before either the next break keyword or the next case. The break keyword is actually optional here. We use it if we want to break out of executing the switch statement. Otherwise, it will keep evaluating until it reaches the end of the block, executing any case that evaluates to true. This example is pretty stupid, but I will add just a few more statements to make it slightly more useful. There is one more feature of the switch statement which works kind of like else. As the name implies, if none of our cases match the predicate, then the code in the default block will be executed automatically. One thing universal about computing systems is that they do not like surprises at all. By surprises, I mean situations which interrupt the normal flow of an application, and the appropriate name to call such a situation is an exception. Unfortunately, if our code does not appropriately handle these exceptions, then the typical result is that the application crashes. The good news is that with a bit of knowledge of situations when a crash is likely to occur, combined with a construct like the try-catch statement, we can often recover the situation appropriately. One thing before I proceed though, sometimes even if we do a really great job handling exceptions, the program will still crash. These unrecoverable exceptions can be caused by hardware or operating system errors or other similar issues. While they are very infrequent, You will find that even the best and most successful applications out there crash from time to time. We are going to create a new method, but this time we will reuse some code from the null safe count occurrences method to save time. I am going to copy and paste the implementation from the other method, then make some changes. So what we have left is our algorithm for counting occurrences. Since we are no longer explicitly checking for a null string, this code would crash the application as soon as it is given a null string. To be specific, when the computer reached the text.toChar statement, it would throw a null pointer exception and the whole program would crash. Since we are aware of that, we can anticipate this null pointer exception and handle it without having this crash occur. As you can see, the try-catch kind of looks like an if-else statement, and it is fairly easy to understand. The computer will attempt to execute whatever code is in the body of the try statement. If an exception is thrown, which would automatically happen if the string is null, then the program will stop what it is doing and resume execution within the catch block. The catch block will quite literally catch that exception, and then it will assign the exception to the variable, in this case variable e. If you are not sure what exception will be thrown, you can make it more generic by using the exception class. I have not explained inheritance yet, but we will look at that in the next part of this course. Sometimes we expect an exception may possibly be thrown, but we do not want to handle that exception locally. Let us copy the try-catch demo method entirely, paste it below, rename it, and remove the try-catch block. Again, we know an exception might occur, but we want the exception to be handled wherever this method was initially called. To achieve this, we add the throws keyword to the end of the method signature before the method body and specify what kind of exception we expect. To test this out, I will add a call to this main method and execute it. As you can see, our exception did actually cause the program to crash. As a quick coding exercise to finish this lesson off, I want you to find out how to stop this program from crashing without removing or changing this call to try-catch-demo-throw, or modifying the method itself. Now you do not need to do anything specific other than simply preventing the program from crashing out. Good luck. In part 2 of this course, I talked about using the static keyword for creating constant member variables. Now, normally I would have gone into detail about how this works, but the truth is that the inner workings of the JVM's various memory spaces is something which even many senior Java developers do not have a clear understanding of. To make things even more ambiguous, these details change depending on which version of the JVM you happen to be using. So please keep in mind for the rest of this lesson that I am going to be focusing mostly on the practical usage of the static keyword, and the theory I do give you is going to be both simplified and generalized, while still somewhat accurate. If you recall from earlier lessons, we use the new keyword when we want to create a new object from a class in memory space. One thing which took a while for me to really understand is that a class itself is not an object, but rather it is used by the JVM as a set of instructions or blueprints for building an object. After the Java compiler creates a bytecode version of a class, such as Sudoku Game, the JVM places said bytecode class in a distinct location in memory. This area in memory holds what we will call class data. Anytime the JVM needs to create an object, such as when we use the new keyword, it will look at the class data and use it to build an object in a different portion of memory space. The main idea you need to understand about the static keyword is that static variables are stored in the same space as the class data. Instance variables, the non-static ones, are stored with the object that they are associated with. There are several consequences to the fact that these static variables are stored with the class data instead of with the object, but the most important one has to do with the ratio of objects relative to static variables. There only exists one copy of a given static variable for any number of objects associated with it. For example, we can create 500 Sudoku Game objects and they will all be sharing that same static variable. That is why in section 3 I told you to be very careful with non-final static variables. If they are not final, they are a prime example of shared mutable state. As for static methods, you can probably guess that they are stored in the class data as well. But actually, all methods for a class are stored in the class data, so the distinction here is less important. Well, I have some more news which you are not going to like. If you search this topic online, you will find entire blogs dedicated to convincing how static methods are evil incarnate because they are difficult to test or they are not considered object-oriented programming. Again, I could get into an extraordinary amount of theory here on those 2 points, but I think that is enough theory for one lesson. Let us look at a few examples and we will try to draw some conclusions from them. A good hint for when to use static methods comes from the Java Math class from stdlib. This class is full of static methods and they mostly follow a simple pattern which we can use as a guideline. They just take in some data, usually a primitive, and return some result in a deterministic way. They may delegate to other static methods. They can do all of this work without relying on instance variables, that is, the non-static variables associated with an object as opposed to the class itself. A common prescription for static methods is that they work great for utility methods. I find this word utility to be a little bit too generalized to be useful, so the above guidelines I gave are an attempt at answering the question of what constitutes a utility method. Using my own definitions for a moment, I find very often that computation logic, which I consider the Java Math library to be representative of, often makes sense to model as static functions. For example, if you look into the computation logic package of the Sudoku app, you will see that the classes responsible for building, validating, and solving a Sudoku puzzle, represented as a two-dimensional array, are full of static methods. In this case, rather than using classes as a means of describing objects, I'm actually using classes as a means of grouping together different functions based on what kind of problems they are concerned with. As mentioned before, static methods represent a somewhat different approach to the object-oriented paradigm. They are a great candidate for solving problems which correspond to mathematical logic, such as manipulating types like primitives, arrays, and strings. However, because they exist independent of objects, they can cause us to lose some of the benefits which we gain by working with an object-oriented language. As for the argument that they present problems for testing, that idea is actually entirely dependent on how you use them. In any case, we will worry about this after I have introduced the topic of testing. Testing is one of the most important and misunderstood topics in the whole field of software development. If you have spent much time looking into the topic, then you will have likely been confronted with an impenetrable set of jargon terms and countless different tools for testing. There really is a lot to discuss regarding testing, but unlike the previous lesson on static methods and variables, I do not actually need to explain much theory to get you started with the basics. In this video, I will explain what testing is in a clear and simple way, why testing is important, how to write tests in Java using a very simple set of tools. Most teachers introduce the topic of testing by explaining some particular tool which you can use to test your code. This is an awful way to introduce this topic, as these tools are often complicated, but the principal idea of testing is so simple that a child could understand it. So what is the principal idea behind testing? We have some piece of code, such as a method or series of methods. In testing jargon, this is known as a unit. We decide ahead of time how that method should behave. Should it change the arguments we give it in a specific way? Should it return a specific value? Should it invoke other methods? Once we have decided how it should behave, we set up a test environment, such as a JVM, we call that method or unit, and we see if its actual behavior matches our expected behavior. In order to put the steps I just mentioned into practice, we will write what I consider to be the simplest kind of test possible for a Java program. Before proceeding, you will want to have the demo code for Part 3, Lesson 6 open. Begin by opening up simplejavateststarter.java. Here I have a simple main method. Since I want to add multiple tests, I will use this main method as an entry point to call each test, which itself will use a method as an entry point of execution. The motivation for writing this current test is as follows. One of the ways we know if a Sudoku puzzle is complete is whether or not any row, column, or 3x3 subgrid of the Sudoku grid has repeated numbers. If each row, column, and 3x3 subgrid contains the numbers 1 to 9 without repeats, then we have a valid, complete Sudoku grid. Therefore, we know logically that we will require a method or series of methods to implement some kind of checking algorithm. Now, in order to save our progress and to help us understand what we are doing in this test, I have written a comment above which reflects the motivation of this test in simple language. This may seem like a waste of time to some, but the fact that we can describe the functionality in plain, simple language actually means that we have already begun to design the implementation. As you write more complicated tests and units, you will see that this step can be critically important. Remember, earlier I said that the way we test a method is to compare its actual behavior to some kind of expected behavior. This process can change, but based on our description, we should expect that a collection of numbers 1 through 9 without repeats and a collection which has repeats should give us distinct behavior. Let us create some data to represent this. I know I am working with arrays, but I also know from experience that the list class in Java has a handy method which can count the occurrences of a specific item in the list. Next, we want to be able to make some assertions. Since our concern here is whether or not a collection has repeats, a Boolean is clearly a safe and legible option. This may seem strange, but we are going to write our assertion statements before writing our method. We could actually just print out a message to the console telling us if our expected result matched the actual result, but Java has a handy construct called the assert statement, which is designed for this exact scenario. If the expression beside the assert statement evaluates to false, then the program will crash. Outside of a testing environment, crashes suck, but inside a testing environment, crashes are how you establish when exactly your program is working properly versus when something is broken. Note, I have written these assert statements in a very verbose and easy to understand way, but they can be simplified. The next step would be to implement the method we want to test. To save time, I have included this method as a static method within game logic, which does not need to be created in order for us to call that method. After you have implemented your method, it is time to run your tests. Again, you may have made some kind of error in the implementation and the test may fail. It just means that you need to keep modifying your implementation until all tests are passing. If all tests pass and you are confident that you have covered every expected behavior, then you have logically proved that your implementation is working properly. The first time I heard about this idea of writing tests before writing implementations of my program's functionality, it looked like a whole bunch of extra work without much benefit. What I did not understand until I spent a significant amount of time using this approach was that it was actually saving me more time than just writing the implementation and testing it by launching my programs. Now, testing your program by launching is a totally valid way to test and something you should do. However, it almost invariably takes a longer amount of time to deploy and manually test a running program than it does to deploy a programmatic test suite. The other benefit is something that I alluded to earlier. When you start to design very complicated programs by starting with a plain language description, then a series of steps in plain language, you will actually be designing things ahead of time in a way which is easier for most humans to do than designing the different parts by just trying to write the implementation directly. Again, this may not seem obvious in very simple applications, but I guarantee you when you start to write more complicated applications and units that this approach will help you out. There are more tools for testing Java code than I can count, but a very good industry standard tool is JUnit. JUnit integrates well with most IDEs and build systems, and it can give you more detailed information on failing tests than just using assertion statements. If you would like to have a look at JUnit in action, check out the test sources for the Sudoku demo application. There is a lot more to testing than what I have mentioned here, but my hope is that by keeping things simple, you will be able to understand in a general way what all of these different testing tools hope to achieve. In this part of the course, I will discuss 3 critically important tools in the toolbox of any Java developer. In fact, what I will teach you in this section will improve you as a developer in any high-level programming language, as the concepts here run far deeper than even the scope of programming languages. In this video, I will talk about what I like to call the theory of abstractions. My goal is to get you to understand philosophically what an abstraction is, as this knowledge is critically important to using inheritance, interfaces, and abstract classes effectively. In subsequent videos, I will show you real-world examples and problems I have solved with these tools, and explain in clear and simple language when each tool is appropriate. Since concepts in computer science are built upon mathematical and logical observations of reality, we as programmers spend our time modeling different aspects of reality in a very concrete way. That is, in code. These same concepts pop up in all different fields of study and work, and that is good for two reasons. Firstly, becoming a good programmer will make you better in all kinds of different ways outside of the field, assuming you can employ the lessons you've learned. Secondly, it means we can learn from other, simpler examples and fields which do not have tendencies to rely upon extraordinary amounts of jargon. I mention this so that you can understand why this whole lesson will seem non-technical in nature. Once we get to the technical and practical stuff, I am confident you will already understand what we are trying to achieve in a very clear way. To begin, let me share a simple definition of an abstraction outside of the field of programming. An abstraction is a less detailed representation of a part of reality. Rather than spending a bunch of time breaking this definition down verbally, let us look at some examples of abstractions in daily life. Suppose you are traveling to an area and you have heard that it is a habitat of a particularly deadly kind of snake. Not wanting to take unnecessary risks, you wish to learn more about the snake. One way to become capable of identifying this snake would be to hire a guide to help you find one. However, while supporting the local economy is great, you could also just search for some images of the snake online. An image of a snake is an abstraction. They have enough details about a part of reality, in this case, a snake, to give you information that can save your life. Here's another example. Let us say that you have a child and you take that child to the zoo. The child is particularly fascinated by bears and asks you if he or she can have one. Now, outside of Russia, it is not common to encourage your child to play with a real bear because that can be very dangerous. Neither wanting your child to come to any harm nor to be completely disappointed, you settle for buying a stuffed bear. The stuffed bear is, of course, an abstraction of a real bear. It has enough detail to keep your child happy and safe. Now that you have an idea of what an abstraction is, I encourage you to take a moment to consider how they are such a fundamental part of reality that they give rise to the ability of information processing systems such as computers or human brains to actually function. Computers use binary digits to represent whatever kinds of abstractions we tell them to. The human brain uses electrical impulses and chemicals to represent more detailed abstractions such as sounds, images, emotions, etc. In summary, the ability to model or represent different aspects of reality, keeping enough details to still be useful, is arguably as important as the physical reality which these abstractions are based upon. As you'll see in subsequent lessons, they are just as important for designing good programs. Inheritance is a mechanism by which one software entity, such as a class, can inherit implementation from another software entity. Inheritance also provides a weak mechanism for abstraction in the programming sense of this word abstraction. In this video, I will explain what I just said using some useful examples, and we will also learn how to use inheritance in Java to improve our code. But before we get to that, I need to teach you a bit about how type hierarchies work so that you can become familiar with the basic terms and definitions within the topic of inheritance. In part 2 of this course, I introduced the idea of type theory, so I will be assuming you are somewhat familiar with what I mean by classes and types. Building on those ideas, type theory is essentially the process of classifying different things based on what is or is not common between them. Now, be aware that I use the word class and type somewhat interchangeably when we are not talking about Java classes specifically. Type theory is also a way of describing the relationships between these different classifications. While I normally try to avoid jargon, there are some common words that programmers use to describe these relationships, and I would be setting you up for confusion and embarrassment if I did not introduce you to them. Here we have a basic classification of different exercises. At the top of our class hierarchy is what we call the base or root class, and it can be thought of as the point of commonality among all of these classes. Below, we have what we call child classes or subclasses of exercise. Both terms are commonly used. Notice how when I described them, I explicitly said that they were child classes of exercise. That is because, relative to the classes below them, we would call them parent classes or superclasses. In case you are wondering what sub and super mean, they are Latin prepositions for under and above. These are the most commonly described relationships, but some people will also say that cat stretch is a grandchild of exercise, or that aerobic exercise is the aunt or uncle of cat stretch. We could also say that running and walking are siblings. To return to a Java-specific discussion, OOP languages are designed to build these kinds of class hierarchies, so much so that we use the word class to describe an object in a hierarchy. Please open up the source code for Part 4, Section 2 in the demo repository. As an example, what we have here is a representation of that same class hierarchy. Simply by using the extends keyword, we can indicate a parent and child or super and subclass relationship. This relationship is known as inheritance, and the extends keyword is how you implement inheritance in your code in Java. The effect of this is that any non-private variable or method will be accessible to the inheriting class even though they are not defined within the body of the inheriting class. Let us look at a quick example. Here we have created a new object from the squats class, and because squats inherits from exercise, which defines a getExerciseName method, we can use that method to print the name. Whenever a superclass requires some kind of arguments, such as exercise name, we need some kind of way to have the subclass pass these arguments from its constructor to the constructor of the superclass. The way to achieve this is by using a special reserved method called super. When you call this method, it will invoke the constructor of the next superclass up, and it expects the appropriate arguments for that constructor. In hierarchies with multiple descendants like this, you may need to make several subsequent calls to super in order for the arguments to satisfy the constructors of every class in the hierarchy. This method is also used to invoke overridden methods, but we will look at that when we get to abstract classes. As should be clear at this point, we use inheritance when we want to share implementation between a set of classes. To be specific, by implementation, I mean variables and methods, including method bodies. When we build desktop or mobile applications in Java, we inherit basic user interface implementations from platform libraries like Swing, JavaFX, or the Android SDK. For example, the entry point for my Sudoku application is actually a class which extends application from JavaFX. This class contains implementations for interacting with the operating system to start and stop the application, and it also gives me access to this stage object, which represents the primary window of an application. As you can see, inheritance is an extraordinarily useful tool which can save us an extraordinary amount of time. Although inheritance is mostly a mechanism for sharing implementation, it can also work as what I like to call a weak mechanism for abstraction. You will hopefully understand what I mean by weak after I explain the next concept, interfaces, which I call a strong mechanism for abstraction. However, let me be a bit more specific about what abstraction means in the context of programming languages. Abstraction means hiding some details of a class, variable, or even a method from the parts of the system which use them. Now, anyone who has built a complicated system will understand this intuitively, but I recall from my early days asking the question, when is having less details ever a good thing? We will look at several situations both in this part of the course and the next part to demonstrate this to you in code. For now, let us look at a very simple yet very practical example of abstraction using inheritance. Before proceeding, please open up the file called Inheritance Starter in the demo repository. There are two goals for this exercise. We want to be able to place several different kinds of exercises in the same data structure. Secondly, we want to iterate through the data structure and print out the different names of each exercise. Let us start by creating some new exercises. Next, we will create a list of exercises. We will use an array list data structure, which is less memory efficient than a normal array, but much simpler to work with in many cases. Now, in case you are wondering, yes, ArrayList is a child of the list interface. This is beside the point of this example, but a good general rule is to keep your reference types as abstract as possible. That does not mean you must always use the abstract type. Sometimes the details do become important. Now, the real magic happens here. As you can see, even though we specify that this is a list of type exercise, every type here is a descendant. The key point is that as far as our list data structure is concerned, it does not know or care what the actual type is. Earlier I said that we should, as a general rule, reference types by their most abstract reference that still allows the program to function. Now we will print out each argument. This is a very rudimentary example, and some of you may still be unconvinced of the power of abstraction, but I am far from done. Like I said before, inheritance is actually a weak form of abstraction, but it is a great way to share implementation. As we saw in the previous lesson, inheritance is a mechanism for sharing implementation. I define implementation as either a variable or a method, including the method body. We also saw that inheritance is a weak mechanism for abstraction. Conversely, interfaces are a weak mechanism for sharing implementation, but a strong mechanism for abstraction. In this video, we will further explore these ideas of weak and strong mechanisms and get into a practical example of interfaces, which will be common for anyone building GUI applications on desktop, mobile, and web. The first principle to understand about interfaces is that they allow us to share what I will call behavior among classes. Now, in the context of programming, I mean something very specific when I say behavior. I define behavior strictly as meaning that we are sharing all parts of a method except the method body. If we were sharing the method body, that would be sharing implementation. Until you look at a practical example, this can seem like a rather pointless thing to do. Is it not just creating extra work that we have to do later? We will see soon enough. Interfaces, as discussed before, are essentially just classes which allow methods to be defined but not implemented. We call these unimplemented methods abstract methods. Now, for technical accuracy, there is actually a feature of interfaces which allows fully implemented methods to be written, and this feature is called a default method. I will not go into detail on them as they are designed to help in maintaining old code bases, which does not concern us, and their existence confuses the original purpose of an interface. Here we have an interface called iEventHandler, which defines an abstract method called handle. We can add as many abstract methods as we want, but just one should suffice for now. You may have noticed that we have some angle brackets here with a T between them. You may also notice this T showing up in our handle method. This is what is known as a generic type. Essentially what we are saying is that we want whatever class which implements this interface and its functions to decide what type will be used. Now, I could actually use whatever name I want here as long as it is not a reserved keyword like new or void. However, if I pick a name like event, we will very likely have conflicts with other types that are either defined within this project or the libraries which this project uses. Therefore, by convention, we usually use a single capital letter such as T for type. Now we will look at implementing an interface. Go ahead and open up Interfaces in Practice Starter.java in Part 4, Lesson 3 of the demo source code. We will be making our event handler impl class implement the iEventHandler interface. Now, I have created an enum here to represent different events one might expect from a desktop system. Obviously it is just for demonstration purposes, but I do actually like to use enums for this purpose, assuming there is not an extraordinarily large number of elements required for the enum. The way in which you make a class implement an interface is via the implements keyword. Because we also specified that this interface expects some generic type to be defined in the class which implements it, we must do that here. As you can probably guess, we will use our event enum. My IDE is now complaining that I have not actually implemented the abstract methods defined in the interface. I could manually type it out, but instead I will click on the red underlined text, hit Alt-Enter, and select Implement Methods. In order to avoid confusion, anytime we implement an abstract method, we must include this special annotation @overrides. This will tell the compiler and IDE where to find the implementation of the abstract method, and it also tells us that this method comes from an interface or abstract class. As a bonus tip, enums like this work great with switch statements. We have seen how interfaces are built and how they work with classes using the implements keyword. However, the most important piece of this puzzle is being able to identify situations where an interface is useful. In the demo Sudoku application, I've written a class which does the work of building the user interfaces and listening for different events which represent the ways in which the user can interact with the application. This is a side note, but an important feature of interfaces is that we can implement as many interfaces as we want, but we can only extend from one single parent class. Java does not allow multiple inheritances. Anyways, in order for this class, userInterfaceImpl, to receive events from the operating system about when a user interacts with the application, I have implemented the event handler interface. Unlike the one we saw previously, this interface is actually defined in the JavaFX library, which is a core Java library for building user interfaces. So here is a primary case. We need a way for the JavaFX code to send messages to this class which I wrote. I achieve that by making this class implement the event handler interface and registering that interface with every part of the application which the user can manipulate. For example, in this app I build a text field for every square in the Sudoku puzzle. In order to get this user interface class to be wired up to every different text field, I add this userInterfaceImpl class to every text field by using the setOnKeyPressed method. Notice how when I click between the argument brackets of this method, it tells me that it requires an event handler. Well, remember, this refers to userInterfaceImpl, and userInterfaceImpl implements event handler. Just to really hit home this point about weak and strong mechanisms for abstraction, it is worth pointing out a key feature of interfaces. Unlike classical inheritance and the other topic we will look at next, abstract classes, interfaces allow us to share behavior among classes that do not need to be within the same class hierarchy. Further, what if I decided to build a second user interface screen of my Sudoku app which displays user statistics like how many games they have won, lost, and various other records? In this case, this other statistics userInterfaceImpl will necessarily need to share the behavior of being an event handler, but it will also need to implement that behavior in a different way. In short, less sharing is more abstract and more sharing is less abstract. One final note. Interfaces have very important uses in software architecture, which we will discuss in Part 5. Before I proceed, if for some reason you have skipped ahead to this video and neglected to watch the lessons on inheritance and interfaces, then you need to go back and watch those videos. I have prepared all lessons in this course to follow the most logical progression I could manage, and this lesson on abstract classes will only make sense if you understood the main ideas of those videos. I am referring to the difference between sharing behavior and implementation, which have very specific meanings. There is also the main idea behind abstraction, which I explored in the first lesson of Part 4. For those who have dutifully followed along with these lessons in order, I have some very good news. I will only need to spend a moment of time explaining theory, and after that we can get straight into practical examples. We saw that inheritance via the extends keyword allows us to share implementation, and implementing an interface via the implements keyword allows us to share behavior. Both tools will allow some degree of abstraction relative to how many details they share. A limitation of interfaces is that you may not share variables. A limitation of classical inheritance is that you may not define abstract methods. Abstract classes are simply a tool which will allow you to share both behavior and implementation. If you have ever wondered when to use them, well, you now know. If you have a problem that can be elegantly solved by sharing both behavior and implementation, then an abstract class is very likely the best solution. We are now going to build part of an abstract class that comes from an actual problem in an actual application I built in the past. The very first full Java application I built was a workout logging tool. Please open up the class called Exercise Starter in Part 4, Lesson 4 of the demo source code. Also, please follow along in your preferred editor using that file as a starting point. As you can see, I have started us out with some basic variables common to different kinds of exercises. As a reminder, the protected access modifier allows visibility within subclasses. The problem we need to solve is fairly straightforward. Our behavior is that we want to be able to print out the data for a given exercise session in a nicely formatted way. However, to avoid confusion, we need to change the implementation of this behavior to account for different kinds of exercises. Here's an obvious but good general rule for creating an abstract class. Whatever changes across subclasses, make it an abstract method. Whatever stays the same across subclasses, implement it in the abstract class. First, let us add the abstract keyword to our class declaration. Next, we will write a method to get the formatted data of an exercise. A good option for building longer strings is to use the string builder class. Every exercise output begins with a name, so we can start by appending that name to our string builder and adding a new line character as well. At this point, our output changes, so this is where we need to perform our abstraction. I could return a string from our abstract method, but since SB is an object, we can also pass it into the receiving method and just keep appending to that same object. If that seems confusing at all, revisit Section 3, the lesson on pass by value. In case you are wondering, the word set is referring to exercise terminology in this case. While we are here, let us finish off this implementation. When we are done with our string builder, we use the toString method. I'm going to let my IDE generate a new method. That is all we need to do here. Next we will implement a child of our abstract class. Go ahead and open up barbellexercise.java in the demo source code. We will not be implementing every kind of exercise, but we will implement this one. Since abstract classes are a form of inheritance, we use the extends keyword just like a regular class. Now that we have specified the parent class, my IDE is complaining that it does not implement the abstract method defined in the parent. I will fix that by clicking on the red underlined text, hitting Alt-Enter, and then Enter. Again, Java is a terribly verbose language, so I will let my IDE do the heavy lifting by using Alt-Enter again. Now all that is left is to implement our abstract method. Every time a set of a given exercise is complete, we record the time or number of repetitions and the weight of each set in the repetitions or time array and the weight array respectively. Now, I did not actually just use two arrays to represent a set in the real app, so understand that this is a simplified version. In any case, we need to loop through each set and print the data appropriately. Keeping in mind our desired output, we will start by appending the number of repetitions or time at the current index. Next, a space. Next, a static constant string inherited from the abstract class. An @ symbol with spaces. The weight at the current index. Another string constant. And finally, a new line character. That is all we need to do. Remember, the string builder object is from the abstract class implementation, so we do not need to return anything. Also within these sources, you will find a main method within abstractclasses.java which I would like you to fix up and execute. I have also included a complete version of abstract exercise in case you get stuck, but you can use whatever you like. As promised, I wanted to end this section by giving you a quick reference guide to knowing when to use each of the 3 tools we have learned about here. To make it practical, I will phrase things in the form of simple questions you can ask when you face a problem that might be solved using them. I want a set of classes to share implementation. Use classical inheritance. I want a set of classes to share behavior. Use an interface. I want a set of classes to share behavior and implementation. Use an abstract class. The topic of software architecture, similar to the topic of testing, is full of confusion, bias, and misunderstanding. Part of the reason for this complexity is that there are many different topics to get into. Another reason is because many teachers do not understand software architecture much beyond just parroting what other teachers say about it. In my case, most of my knowledge of software architecture has come from thousands of hours spent building programs. As such, I am able to explain things in a unique way without leaning on too much jargon. We will not cover every topic in the field, but there is one principle in particular which I've come to understand as being the most important principle in software architecture. In the following lessons, I am going to show you this principle and how to apply it to everything from individual methods up to entire projects. But first, I want to give you the simplest analogy I could think of to explain separation of concerns. The following is a true story. One day I was walking to work and I saw that a sidewalk, or footpath as they say outside of North America, had been replaced. The old sidewalk looked something like you see here, and I was happy to see it replaced because I kept scuffing my shoes on the uneven surface, and back then it was part of my job to have well-kept clothing. The new sidewalk looked like this. Instead of a single continuous layer, it was separated into different pieces. Being an obsessive overanalyzer, I asked myself the question, why build sidewalks in different pieces like that? I did not know it at the time, but the answers to that question captured the essence of why one applies separation of concerns in any interconnected system, from software systems to hardware systems to businesses to sidewalks. A modular system, that is a system which applies separation of concerns, provides these benefits. If one part breaks, it is easier to find the fault and to fix it. It is easier to build each part in isolation of the other parts. It is easier to test each part in isolation of the other parts. It is easier to name each part. There are other benefits, but that should suffice for now. Let us contrast this with a continuous, or as we say in software development, monolithic system. If one part breaks, the integrity of the entire system often breaks. Because of that, it can be difficult to isolate the origin of the fault. In most cases, you must build the whole system or most of the system before you can test at all. It is difficult to give a good descriptive name for something which does everything. It is often highly difficult to read and understand the system, even for the people who built it. I could go on, but the point should be obvious by now. Before we finish this lesson, I wanted to address something for those of you who are not necessarily absolute beginners. If you really are an absolute beginner, do not worry too much about what I'm going to say next. I will explain it in detail later. The most common question I am asked during my live stream Q&A videos takes the form of, Ryan, what is the best software architecture? Or, is Model View ViewModel better than Model View Presenter? What about Model View Controller? I thought I would answer that for any of my students who want to know and might feel disappointed that I will not be going into the specifics of any particular front-end GUI architecture. The answer I always give is that the best architecture depends entirely on the feature of the application you are trying to build. In other words, there is no such thing as the best architecture for every situation. In fact, I will use whatever combination of these styles I feel is most appropriate. So do not worry, in subsequent lessons I will teach you the principles common to all of these architectures. The perspective of applied separation of concerns we will look at in this lesson deals with methods, or functions as we typically call them in other languages. The good news is that there is nothing technically complicated to understand here. All we are doing is breaking down large methods into a series of smaller methods. If you're wondering why we want to do that, I gave you plenty of reasons in the last video, but I still think it is worth showing you exactly what I mean in code. The general idea here is that we want to avoid giant methods as much as possible. Giant methods are difficult to read, difficult to write, difficult to test, and difficult to name. In order to demonstrate an extreme example of this problem, I went through the class in my Sudoku app which is responsible for drawing and interacting with the user interface. I took the code for drawing the UI from each helper method and stuck it all right into the constructor. I took away all of the static uppercase constants and replaced them with hard-coded values. I also renamed a bunch of descriptive variable names I had from before to some very short ones and got rid of any line comments to explain anything I thought might be confusing. In fairness, short variable names, a lack of comments, and a lack of constant values is a separate issue, but they all represent either a lack of understanding or a lack of effort in writing good quality code. The concept of a helper method is very simple, and it follows a principle which you will see repeatedly in this section. Start from general details and work towards specific details. The constructor of this class has the general goal of initializing whatever needs to be initialized in order to begin a new game. The first 3 lines here initialize member variables, which I consider to be a unique concern. After that, I call the initialize user interface method, which does exactly what it says. Instead of one giant method which contains every line of code to draw the UI, I look at the UI as a series of layers of components. Each method is concerned with setting up one of those components. Now, because we are dealing with a large number of UI elements, my methods are not always tiny. That is okay as long as they each have one particular concern. I am not a big fan of using acronyms, but a good simple one to follow is DRY, or Don't Repeat Yourself. The idea is very simple. Look through your code and pay attention to anything that looks repetitious. Very often, but not always, you can pull that repetitious code into its own helper method. For example, as I was writing this lesson plan, I noticed some repetitious code in the drawGridLines function. This method is responsible for drawing the lines on top of the puzzle background which form the grid. Notice how these method calls are identical except that their arguments change? That is a clear case of repetition, and I ended up creating a helper function to handle this situation a little more elegantly. Sometimes you have a method which is useful in multiple different classes. In this situation, a good idea is to use a static method like we discussed in section 3. For example, 2 very common methods in the back end of this application are to take the values of one grid array and copy them to another array, or to create and return a new array. Knowing this, I have pulled these methods out into a separate class which just contains some static helper or utility methods. As mentioned previously, another benefit of SOC at the level of methods is that your code becomes much easier to test. The logic required to generate a new, valid Sudoku game is actually rather complicated and delicate. In truth, I also tend to make lots of small errors, which has been a recurring theme in my life. I have never failed a math test, but I do not recall ever getting 100% because I always make some little arithmetic errors here and there. In order to account for those, I made sure to decompose my method into distinct parts so that I could verify each part individually instead of building mistake on top of mistake on top of mistake. Some of you will have heard of 3-layer architectures such as Model View Controller, Model View Presenter, or Model View View Model. Whether or not these are new terms to you, I am going to teach you about the fundamental separations of code that give rise to these patterns. The truth is that it is not so important that you follow any specific pattern. No pattern works great in every situation. What is more important is to follow the principle of separation of concerns. Doing so will help you understand and apply concepts from each of these common patterns, but it will also help you understand when it is appropriate not to follow a pattern. In fact, if you study and practice software architecture long enough, it will become clear to you that complex applications simply cannot be divided into just 3 layers. Some of the things I say in this lesson will seem a bit too restrictive, tedious, or like they just create extra work. What you have to understand is that the consequences of not following these rules will scale with the size and complexity of the program you are writing. This is all practice for the big show, and if you really do not believe me, I encourage you to build a medium-sized application that does not apply separation of concerns. When I started out as a programmer, I had almost no direction, and I did exactly that. Those painful memories and experiences of having to rebuild an entire application just to add one new feature will always stay with me. Just to clarify, the term layer in software architecture has to do with what a given class is concerned with. Every three-layer architecture you have seen represents a fundamental separation of three kinds of code. Code which manages the user interface, or view classes. Code which provides structured storage and access to data, or model classes. Code which coordinates the other two layers in a logical fashion, which I like to call logic classes. Now, I will break these layers down even further, but these three distinctions are a good general way to think about your code. The main styles, such as MVC, MVP, and MVVM to a lesser degree, are in a broad sense always a breakdown of these three layers. I am often asked which one is best, but the truth is that for every style, what makes it good in certain situations makes it bad in other situations. To make this even more confusing, people do not even build them the same way. I have written about these situations in various articles, but like I said, in this lesson we will focus on the reasoning process rather than the specific styles or patterns. If you are building something with a graphical user interface, your app will need to interact with tools such as JavaFX or Swing for Java Desktop, Java EE for web apps, or the Android SDK for mobile. There is an important term to describe a kind of class which must necessarily deal with some kind of external driver or library, such as the UI, a database, or some kind of system service. We say that this class is tightly coupled to whichever driver or library. An easy way to know what a class is coupled to is to check the import statements it possesses. In the demo Sudoku app, my user interface impl is tightly coupled to JavaFX. Although a Sudoku game looks visually very simple, we have 81 different text field objects to draw, listen to for inputs, and update appropriately. These problems all have to do with interacting with a user interface, and therefore it makes sense to separate these problems from others, such as generating a new Sudoku puzzle or checking if the current one is complete. The standard name for this kind of user interface class is a view, and thus it conceptually fits into the view layer of a typical architecture style. One of the biggest difficulties with view classes is a direct result of their tight coupling. They are difficult to test. Unless you use some tools which mock or create a fake version of their libraries or frameworks, the only way to test them is to actually build and deploy an application. One final note before we move on. This application has one screen, so I have included the style information inside of this view class. However, in an application with multiple screens, I would follow the dry principle and pull any style information into a separate data structure that can be shared globally. I have already defined what model means extensively in part 2 of this application. Recall that this word in general describes anything to do with structured storage and access to data. However, when speaking of software architecture, there is some confusion about this word which I will discuss. In a historical context, this word model, as defined in the original model view controller pattern, did not refer to a class which implemented long-term storage. People still argue about these definitions to this day, but I think it is better to understand each definition rather than wasting time arguing over which one is correct or incorrect. I like to categorize data, or state, in an application in two ways. First, we have user session state. This kind of data lives only as long as the program or some particular screen of the program is running. To give you a clear example, if I remove the long-term storage from my Sudoku app, the user can still complete puzzles as long as they keep the app running. The time during which a user is actually using the app can be thought of as a session. The other kind of state has the potential to persist longer than runtime. The Sudoku app actually stores the state of the Sudoku puzzle so that the user can close the app and continue the same puzzle later. Anyways, the reason I bring this distinction up is that these different kinds of states and the parts of the model which implement them need to be treated differently. Persistence mechanisms, such as databases, network adapters, file storage, etc., should be hidden behind an interface. What I just told you in technical terms is to employ the repository pattern, which is more generally known as the facade pattern. Design patterns is a topic too big to go into detail with here, but understand that similar problems are often best solved with similar patterns. Doing this will effectively allow you to hide the details of your persistence mechanisms from the rest of your application. To be clear, what I am saying is that if you do not use interfaces anywhere else, I really recommend you use them as a bridge between what we can think of as the front end of your application versus the back end. In fact, the front end should have no idea whether the data it receives and inputs is coming from a file, a database, or a cloud server. Remember, all we are doing here is applying separation of concerns. Finally, we come to logic. Again, some good news. I have already explained to you the different types of logic. We can think of control logic as a controller or presenter, or honestly even a view model depending on how you use it. It handles events and it coordinates between the other layers or classes. In this Sudoku app, I have a class which is literally called control logic. As you can see, it holds references to the view and the storage by interface. This makes it easier to test as I do not need to deploy the application and have a real view or real persistence mechanisms behind these interfaces. Another subset of control logic, which I suggest you keep separate from other things, is what I like to call build logic. This relates to the term dependency injection if you have ever heard of it. Martin Fowler, my favorite authority on software architecture, summed this up beautifully by discussing the principle of separating configuration from use. As for computation logic, we are of course talking about classes or methods which validate user input, solve equations, or build Sudoku puzzles. At first I just had one single class which was supposed to encapsulate all of the computation logic necessary for my Sudoku game to function properly. It turned out that this was actually a pretty complicated process, so I ended up creating two more classes to separate things even further. The game generator class generates a completed valid Sudoku game. Now, since a completed Sudoku game is not really fun to solve in any sense of the word, I needed to unsolve the game. It turned out once again that this process was kind of complicated. At first I thought I would just remove 40 numbers, but it turns out that you cannot just do that and expect your puzzle to be solvable. So after I removed the 40 characters, I fed the resulting grid into a class called Sudoku Solver, which would tell me if it was solvable. Anyways, why I am telling you this is to share my thought process. The more I learned about the problem of generating a new Sudoku game and validating an existing one, the more it made sense to further divide this logic up into distinct classes. Admittedly, some of these methods are still pretty huge, but this is a result of working with algorithms that require a large number of steps. At the very least, you will notice that I have written all kinds of comments to remind myself what each method does in detail. I am a big fan of clean architecture. I have studied solid principles for years, I have tested out all major architectures, and I have even seen how inadequate three-layer architectures tend to be outside of very simple scenarios. While I hope I have done a decent job of sharing some of that knowledge, the truth is that you will never understand these things clearly if you do not apply them by building applications. Do not be afraid to try different things, and while having preferences is okay, do not become dogmatic about any particular architecture. Moving into an even broader perspective of separation of concerns, we will look at how to appropriately organize the source files of an application. I will discuss two approaches which are common to use, and my own approach which features ideas from different styles. I recall being quite confused about the term package in the context of programming at least, and how exactly a package was different from a regular old directory, commonly known as a folder. To answer that question in short, there is no difference. A package is a directory. If you wish to test this idea and you have an IDE, just look at one of your projects in a regular file explorer. With that being said, it is important to understand that the directory structure or package structure is actually important for several different reasons. Aesthetically, they help developers to have an easier time organizing and reading software applications. We will revisit that point, but the other reason they are important is that they can represent a way to identify an application. Something which you will see when building Java applications on just about any platform, desktop, mobile, or web, is a main package. Typically, within this main package will be a Java package. Within this Java package, you will find a series of packages which combined form the package name of an application. They almost always follow a convention which looks something like a reversed website domain URL. The assumption is that you or the company you work for have registered a domain, and that is the domain name you would use here. For students, it is okay to use whatever you want, but a common convention is to use com.example.someApplicationName. The purpose of this package name is to provide a unique identifier or signature for a specific application. Obviously, you should not reuse the application names even in your learning projects. When it comes time to host or publish an application to things like an app marketplace or web server, your application's package name will be used by that service as a unique identifier. Therefore, you will want to be certain that you have chosen an appropriate package name before doing so. Apart from package names, we have what are called package structures, which tend to be related to your software architecture. A common approach is to put files which belong to a particular layer into a package labeled according to whatever layered architecture you are following. This approach is better than nothing and works okay in smaller projects, but it scales very poorly to complicated projects. Also, it is not always clear which layer a class really belongs in, especially if you are not applying SOC in your classes. Package by feature is much more appropriate for projects that have multiple different features. A feature can be loosely described as a particular screen of your application. For example, in Facebook you have Home, Profile, and Find Friends features, to name a few. The idea with package by feature is that you place any file which has to do with a particular feature in the same package. Especially in medium to large scale projects, I find this setup to be much more organized than package by layer. However, the problem with it is that it does not account for source files which need to be used in multiple different features. Having the same source file in multiple feature packages is a terrible idea, so something needs to be added to this style. Here's a simple way to lay out your source files in packages that will scale to any size of project. Any files which only concern a particular feature should go in a feature level package. Any files which are shared among several features should go in an appropriately named package which sits outside of a particular feature. Do not be afraid to make several packages that sit outside of features if you have lots of shared files that have different concerns. All of this is just common sense. Separate things that are general from things that are specific and give them good names. In the past few lessons on software architecture, I have done my best to pick the most easily understood and practically useful topics that I could think of. As you saw, in my opinion, the single most universally applicable and important topic can be summarized with the phrase, separation of concerns. With that being said, there is one more thing I wanted to discuss, which is a process that occurs before writing a single method or class. I recall from my first year as a programmer that I really wished I had some kind of process I could use to design a new program. If you're in the same boat, then I think you will enjoy this video. The first step in designing any new application is to perform what I like to call in general problem domain analysis, or PDA. There are different ways to do this, such as problem statements or user stories, but both of these approaches are fundamentally the same thing. To put this into simple terms, a problem domain is some area of expertise, field of study, or aspect of a business which you, as the programmer, must ultimately represent virtually in a program. For example, a calculator program must virtually represent mathematics. A bank program must represent accounts, money, stocks, credit ratings, and so forth. A social media program must represent users, friends, posts, likes, etc. To summarize this whole process, problem domain analysis means two things. What information must my program represent virtually as data? What does my program need to do in order to solve some kind of problem for its users? An easy form of PDA is to write a problem statement. This was the first approach I learned, and it is a quick and simple way to get started. Now, before I proceed, keep in mind that our goal here is not to verbally describe the entire application in fine detail. Start with basic features only. If you follow my lessons in software architecture, adding new features later on will be very easy. Anyways, the idea here is very simple. First, write a plain language description of either your application or a feature of your application. My program will create a Sudoku puzzle which the user can solve. It will store the progress of this puzzle and create a new puzzle after one is completed. Second, pay close attention to the nouns and verbs in your problem statement. The nouns will tell you about what the data structures such as classes, variables, and constants will look like. The verbs will tell you about different logical entities such as methods, classes, and interfaces. From there, you can create a new project and build anything that seems sensible as a foundation for your application's architecture. Another approach which is very common among software professionals is to create what are called user stories. User stories are essentially problem statements, but you write them from the perspective of your users. It is important to apply separation of concerns with each story. Each story should concern one primary noun and one primary verb. To take the Sudoku app as an example once more, as a user, I want to be able to complete a Sudoku puzzle. As a user, I want to be able to store my progress. As a user, I want to start a new puzzle after I complete a puzzle. Afterwards, you will follow a similar process of considering the nouns and verbs. What to do after problem domain analysis depends on your general approach to software development and the project requirements. Some people argue that users will prefer a poorly built application with a good user interface than a beautifully functional and efficient application which looks awful. As much as I hate to admit it, I think there is a lot of truth to that when it comes to recreational or mainstream applications. A pretty user interface will make your application look professional and is more likely to attract the average person. However, this approach can backfire if your app does not function properly, crashes often, or you are simply not able to build your beautiful designs. However, if you are building an application for a very specialized or technical profession, it might actually be very important to be more concerned about the efficiency, data structures, logic, and architecture of such an application. In this case, you should still try to avoid having an ugly user interface, but having a simplistic yet easy to navigate user interface might be your top priority. It all comes down to keeping an open mind and trying different approaches while at the same time paying close attention to the project requirements.